2, 1. We have ignition, and we have liftoff. We have liftoff of the Titan Centaur carrying the first of 2 Voyager spacecraft to extend man's senses farther into the solar system than ever before.
Launched 46 years ago, the twin Voyager spacecraft captured the public imagination as Earth's first ambassadors to the outer planets. They visited mighty Jupiter, ring-bedecked Saturn, gloomy Uranus, and stormy Neptune to lay bare humanity's naked insignificance. The brutalized moons, ring particles clinging to million-mile racetracks, sulfur-belching volcanoes, ice-spewing geysers, craters straight out of Star Wars, and roiling Earth-sized tempests the Voyagers saw captivated us with an exquisitely savage beauty. In recent decades, the missions have made few headlines, but the little spacecraft have continued voyaging outward beyond the wildest dream of scientists. Despite their now archaic memory and transmission systems, the Voyagers remain on the cutting edge of space exploration as the only instruments to ever travel through interstellar space. Transcend the distance of space and time. Voyager 1, the farthest human-made object from Earth, at about 3 times the distance of Pluto from the Sun, still is sending back some spooky data from interstellar space that's leaving NASA engineers scratching their heads. Join us as we get to the bottom of everything that happened and consider what the discovery means for the future of humanity. Voyager 1 almost didn't get off the ground at its launch, as its rocket came within 3.5 seconds of running out of fuel on September 5, 1977. But the probe made it safely to space and raced past its twin after launch, getting beyond the main asteroid belt between Mars and Jupiter before Voyager 2 did. Voyager 1's first pictures of Jupiter beamed back to Earth in April 1978, when the probe was 165 million miles from home. According to NASA, each Voyager probe has about 3 million times less memory than a mobile phone and transmits data approximately 38,000 times slower than a 5G internet connection. To NASA's surprise, in March 1979, Voyager 1 spotted a thin ring circling the giant planet. It found 2 new moons as well, Thebe and Metis. Additionally, Voyager 1 sent back detailed pictures of Jupiter's big Galilean moons, Io, Europa, Ganymede, and Callisto, as well as Amalthea. Like the Pioneer spacecraft before it, Voyager's look at Jupiter's moons revealed them to be active worlds of their own. And Voyager 1 made some intriguing discoveries about these natural satellites. For example, Io's many volcanoes and mottled yellow-brown-orange surface showed that, like planets, moons can have active interiors. Additionally, Voyager 1 sent back photos of Europa showing a relatively smooth surface broken up by lines, hinting at ice and maybe even an ocean underneath. Voyager 1's closest approach to Jupiter was on March 5, 1979, when it came within 174,000 miles of the turbulent cloud tops. Then it was time for the probe to aim for Saturn. Scientists only had to wait about a year until 1980 to get close-up pictures of Saturn. Like Jupiter, the ringed planet turned out to be full of surprises. One of Voyager 1's targets was the F-ring, a thin structure discovered only the year previously by NASA's Pioneer 11 probe. Voyager's higher-resolution camera spotted 2 new moons, Prometheus and Pandora, whose orbits keep the icy material in the F-ring in a defined orbit. It also discovered Atlas and a new ring, the G-ring, and took images of several other Saturn moons. One puzzle for astronomers was Titan, the second largest moon in the solar system, after Jupiter's Ganymede. Close-up pictures of Titan showed nothing but orange haze, leading to years of speculation about what it was like underneath. It wouldn't be until the mid-2000s that humanity would find out, thanks to photos snapped from beneath the haze by the European Space Agency's Huygens atmospheric probe. The Saturn encounter marked the end of Voyager 1's primary mission. The focus then shifted to tracking the 1,590-pound craft as it sped toward interstellar space. 2 decades before it notched that milestone, however, Voyager 1 took one of the most iconic photos in spaceflight history. On February 14, 1990, the probe turned back toward Earth and snapped an image of its home planet from 3.7 billion miles away. The photo shows Earth as a tiny dot suspended in a ray of sunlight. Voyager 1 took dozens of other photos that day, capturing 5 other planets and the Sun in a multi-image solar system family portrait. But the pale blue dot picture stands out, reminding us that Earth is a small outpost of life in an incomprehensibly vast universe. Voyager 1 left the heliosphere, the giant bubble of charged particles that the Sun blows around itself, in August 2012, popping free into interstellar space. The discovery was made public in a study published in the journal Science the following year. The results came to light after a powerful solar eruption was recorded by Voyager 1's plasma wave instrument between April 9 and May 22, 2013. The eruption caused electrons near Voyager 1 to vibrate. From the oscillations, researchers discovered that Voyager 1's surroundings had a higher density than what is found just inside the heliosphere. It seems contradictory that electron density is higher in interstellar space than it is in the Sun's neighborhood. But researchers explained that, at the edge of the heliosphere, the electron density is dramatically low compared with locations near Earth. Researchers then backtracked through Voyager 1's data and nailed down the official departure date to August 25, 2012. The date was fixed not only by the electron oscillations, but also by the spacecraft's measurements of charged solar particles. On that fateful day, which was the same day that Apollo 11 astronaut Neil Armstrong died, the probe saw a 1,000-fold drop in these particles and a 9% increase in galactic cosmic rays that come from outside the solar system. At that point, Voyager 1 was 11.25 billion miles from the Sun, or about 121 astronomical units. 1 astronomical unit is the average Earth-Sun distance, about 93 million miles. You can keep tabs on the Voyager 1's current distance and mission status on this NASA website. Voyager 1 is currently about 15 billion miles away, and at 46 years old, the probe has shown multiple quirks and signs of aging in recent years. The latest issue experienced by Voyager 1 first cropped up in November 2023, when the Flight Data System's telemetry modulation unit began sending an indecipherable repeating pattern of code. Voyager 1's Flight Data System collects information from the spacecraft's science instruments and bundles it with engineering data that reflects its current health status. Mission Control on Earth receives that data in binary code, or a series of ones and zeros. But since November, Voyager 1's Flight Data System had been stuck in a loop. While the probe has continued to relay a steady radio signal to its mission control team on Earth over the past few months, the signal did not carry any usable data. In December of 2023, the Voyager 1 team announced that the spacecraft's malfunction lies with its Flight Data System, or FDS, which is one of its onboard computers. There used to be a backup FDS, but that stopped working in 1981. Because of this issue, scientists are not receiving any science data or updates about the probe's health and status, including information that might reveal the source of the problem, the team explains. Here's where perhaps the greatest trouble with this dilemma comes in. One of the FDS's main jobs is to basically keep Voyager 1's medical records up to date, then work with what's known as the telemetry modulation unit to tell ground control what's going on. But, because the FDS itself is the one malfunctioning, that medical record transmission can't happen. In February 2024, the team believed one possible cause of the issue has to do with the FDS's memory being corrupted by some mechanism that leads its binary code to sprout unintelligible patterns. However, engineers are also considering the fact that it could be a physical hardware failure. After all, Voyager 1's mechanics have been toiling away for multiple decades. Something could have simply broken down, hardware or software-wise. In fact, scientists beamed some preemptive software patches to both of the Voyagers last year, from billions of miles away. And in a slightly more far-fetched scenario, the team also suggests it's possible some sort of energetic particle could have smashed into the spacecraft. If that happened, it might have created what's known as a bit flip, which means a 0 in the code accidentally became a 1, or vice versa. All possibilities are open. That's because, in truth, no engineering data is coming back. It's very hard to isolate the source of the problem. What's more, note that how Voyager 1's greatest achievement is being the first ever probe to venture into interstellar space, where it's surrounded by untouched stardust and blankets of darkness. Yeah, it's extremely far away from us. And that means the message seems to indicate that Voyager 1 may have encountered some kind of foreign object. This could have been anything from a pocket of gas to a stray rock floating in the vast expanse of space. The eerie possibility that the Voyager even had made contact with an alien entity. And that's not wishful thinking. Either way, this spacecraft is currently farther from Earth than any other man-made object in history. In other words, it is embarking on a journey to the unknown. Interstellar space also holds many mysteries, including the nature of dark matter and dark energy, which make up the majority of the universe's mass and energy, but remain poorly understood. Another exciting aspect of interstellar space is the possibility of discovering new forms of life. In some hypotheses, interstellar objects like a rock or just a cloud of dust also may have been alien probes. So, could Voyager 1 meet some unknown force or intelligence out there in the vast expanse of space? Well, we just can rule this possibility out. That's why it's important to consider the potential implications of any strange signals or transmissions that the spacecraft may send back to Earth. And according to the latest update, the mission team received the first coherent data about the health and status of Voyager 1's engineering systems. While the team is still reviewing the information, everything they've seen so far suggests Voyager 1 is healthy and operating properly. The breakthrough came as the result of a clever bit of trial and error and the unraveling of a mystery that led the team to a single chip. After discovering the issue, the mission team attempted sending commands to restart the spacecraft's computer system and learn more about the underlying cause of the problem. The team sent a command called a poke to Voyager 1 on March 1st to get the flight data system to run different software sequences in the hopes of finding out what was causing the glitch. On March 3rd, the team noticed that activity from one part of the flight data system stood out from the rest of the garbled data. While the signal wasn't in the format the Voyager team is used to seeing when the flight data system is functioning as expected, an engineer with NASA's Deep Space Network was able to decode it. The Deep Space Network is a system of radio antennae on Earth that help the agency communicate with the Voyager probes and other spacecraft exploring our solar system. The decoded signal included a readout of the entire flight data system's memory. By investigating the readout, the team determined the cause of the issue. 3% of the flight data system's memory is corrupted. A single chip responsible for storing part of the system's memory, including some of the computer's software code, isn't working properly. While the cause of the chip's failure is unknown, it could be worn out or may have been hit by an energetic particle from space, the team said. The loss of the code on the chip caused Voyager 1's science and engineering data to be unusable. Since there was no way to repair the chip, the team opted to store the affected code from the chip elsewhere in the system's memory. While they couldn't pinpoint a location large enough to hold all of the code, they were able to divide the code into sections and store it in different spots within the flight data system. According to an update from NASA, to make this plan work, they also needed to adjust those code sections to ensure, for example, that they all still function as a whole. Any references to the location of that code in other parts of the flight data system, memory needed to be updated as well. After determining the code necessary for packaging Voyager 1's engineering data, engineers sent a radio signal to the probe commanding the code to a new location in the system's memory on April 18th. Given Voyager 1's immense distance from Earth, it takes a radio signal about 22.5 hours to reach the probe, and another 22.5 hours for a response signal from the spacecraft to reach Earth. On April 20th, the team received Voyager 1's response, indicating that the clever code modification had worked, and they could finally receive readable engineering data from the probe once more. Within the coming weeks, the team will continue to relocate other affected parts of the system's software, including those responsible for returning the valuable science data Voyager 1 is collecting. The team estimates it's a few weeks away from receiving science data from Voyager 1 and looks forward to seeing what that data contains. In the words of Voyager project manager Suzanne Dodd, "We never know for sure what's going to happen with the Voyagers, but it constantly amazes me when they just keep going. We've had many anomalies, and they are getting harder, but we've been fortunate so far to recover from them. And the mission keeps going, and younger engineers are coming onto the Voyager team and contributing their knowledge to keep the mission going." While Voyager 1's groundbreaking discoveries gave us revolutionary views, its success also helps to inspire the next missions with the hope of solving the biggest question of all, that of are we alone in the universe? It's an ambitious project, but one that's well worth it. Currently, we're building the next generation of ground-based telescopes, ushering in the era of 30-meter-class telescopes with the Giant Magellan Telescope and the Extremely Large Telescope, and looking forward to NASA's next astrophysics flagship mission, the Nancy Roman Telescope, which will have the same capabilities as Hubble, but with superior instrumentation, a field of view that's 50 to 100 times as great as Hubble's, and a coronagraph that allows us to image planets within the glare of their parent star's light that are about 1,000 times fainter than James Webb can see. However, even with these advances, we'll only get Earth-sized planets around the nearest red dwarf stars and super-Earth or mini-Neptune-sized planets around Sun-like stars. To image a truly Earth-like planet, an improved observatory with still greater capabilities is required. Thankfully, our technology does not remain stagnant, nor do our visions for discovery and exploration. Each decade, the National Academy of Sciences gets together to outline the highest priorities for astronomy and astrophysics, making recommendations as part of a decadal survey. There are 4 proposed flagship missions were proposed. Lynx, a next-generation X-ray observatory, especially important given the reduced scope of the ESA's upcoming Athena mission. Origins, a next-generation far-infrared observatory, filling a colossal gap in our wavelength coverage of the universe. HabEx, a single-mirror telescope designed to directly image the very nearest Earth-like planets. And LUVOIR, an ambitious giant segmented telescope that would be an astronomical all-purpose dream observatory. While the recommendation was that all 4 of these be eventually constructed, the highest priority mission was a scaled-up version of HabEx, taking features of both HabEx and LUVOIR into account to form the Habitable Worlds Observatory. In many ways, the proposed specification hit precisely in the sweet spot between feasibility, given current technology, discovery potential given what we do and don't know, and cost-effectiveness, incorporating lessons learned from the problems experienced with building and launching the James Webb Space Telescope. The specifications proposed so far are very encouraging and include a segmented optical mirror design similar to what's already in use by James Webb, the same type of coronagraph technology that's presently being developed and tested for the Roman telescope, up-to-date sensors that can control the various mirror segments to achieve picometer level stability, planned compatibility with next-generation rockets that will be flying in the late 2030s or early 2040s, planned robotic servicing of components at the Lagrange Point 2, located 1.5 million kilometers from Earth, and no wholly new technologies that haven't been fully matured prior to the development construction phase. This is extremely encouraging, as it presents an achievable plan that isn't particularly susceptible to the delays and overruns, primarily due to the need of developing wholly new technologies that plagued James Webb for years before its launch. With these capabilities, the Habitable Worlds Observatory will have an excellent chance to reach what's perhaps the holy grail of astronomy, to reveal an actually inhabited planet to humanity for the very first time. With between a 6.0 and 6.5 meter design comparable to James Webb Telescope in size, it should be able to directly image Earth-sized planets around all of the stars within about 14 light-years of Earth. Every little bit of extra diameter counts in this game, because if you can double the radius you can see planets out to, you increase the search volume and the expected number of objects by a factor of 8. In the vicinity of the Sun, there are 9 star systems within 10 light-years of Earth, 22 star systems within 12 light-years of Earth, 40 star systems within 15 light-years of Earth, and 95 star systems within 20 light-years of Earth. With its planned design, somewhere between 20 and 30 Earth-like planets could be directly imaged by the Habitable Worlds Observatory. If there's even a few % chance of life taking hold on an Earth-like world, then this mission will be able to discover our first inhabited planet beyond the solar system. Perhaps, if nature is kind, we might even discover more than one. Because we've already gone through the pain of developing many of the precursor technologies, including the 5-layer sun shield used with James Webb, the folded or segmented mirror design used with James Webb, and the deformable mirror used within the Roman coronagraph, there shouldn't be anything wholly new or novel to trip up the Habitable Worlds Observatory like there was with the Webb. However, all new developments come with risks. The idea of robotic servicing is encouraging, because we've done robotic servicing before, but only as far away as in low Earth orbit. At the distance to Lagrange Point 2, 1.5 million kilometers, even instructions sent at the speed of light have a 10-second round-trip delay. Servicing will require both rocket technology and automated robotic technology that does not exist presently. To achieve our picometer-level mirror alignments is a technical challenge that requires advances far beyond the nanometer-level alignments achievable today. Although this requires only an incremental improvement over existing technology, a substantial set of resources will need to be devoted to it and are currently being devoted as part of the technology maturation process inherent in the design and pre-design phases. One big worry that hasn't necessarily hit the right people's radar is the suitability of the currently designed Roman coronagraph for the Habitable Worlds Observatory. James Webb Coronagraph is performing exactly as anticipated, enabling us to find and image planets that are just 1 part in 100,000 as bright as their parent stars are. The Nancy Roman telescope expects a factor of 1,000 improvement over James Webb, as their deformable coronagraph mirror is being optimized to deal with the interference patterns and stray light that emerges from a perfectly circular coronagraph shape. However, there's a catch. One of the reasons that the Nancy Roman telescope's coronagraph can perform so much better than James Webb's is because Webb has a tiled mirror with a segmented design, while the Nancy Roman telescope will have a single, circular, monolithic mirror. The shape of the Webb telescope mirror is why it has that snowflake-like diffraction pattern around all of its stars and bright point sources of light. That's just a mathematical consequence of the geometry of its optics. But coronagraphs are circular in nature and cannot easily undo the stray light that gets introduced from any sharp edges, including the hexagonal tiles, the corners on the outer edges of the mirror, and the millimeter-sized gaps between the various segments. With a similar design to the James Webb Space Telescope, this seems like a very big problem for Habitable Worlds Observatory to reckon with, particularly since it needs coronagraphy that's successful at the 1 part in 10,000 level to image Earth like worlds around Sun like stars, another factor of 100 better than the Roman coronagraph will achieve. One potential solution is to launch a starshade either with the Habitable Worlds Observatory or even after the fact, to block the star's light before it ever reaches the Habitable Worlds Observatory's primary mirror. Although this is technologically feasible, it's both expensive and limited in its effectiveness. It has to travel some 80,000 kilometers relative to the observatory every time it wants to switch targets. All told, it can potentially help image about 1 or 2 systems per year, but that's the upper limit. A wild solution that perhaps should be considered is not building a traditional segmented mirror, but a series of circles, akin to the optical setup of the under-construction Giant Magellan Telescope. With 7 perfect circles instead of 18 plus tiled hexagons, it has the light-gathering power of the area of all 7 circles combined, but the resolution of the diameter across which the primary mirrors are mounted. With this design, all of the stray light problems from a James Webb-like design are eliminated. The already developed foldable primary mirror technology could still be utilized. The picometer-level stability technology being developed across mirror segments would still apply. Instead of a single secondary mirror and/or a single coronagraph, each of the 7 segments could get their own, and, as a bonus, there would be no wires required to cross the primary mirror optics, as the secondary mirrors could be held in place with wires that went in between the gaps in the circular segments. Precisely why the Giant Magellan Telescope will be the first world-class observatory without diffraction spikes on its stars. With the right design and implementation, we could be looking at a Habitable Worlds Observatory that launches as early as the late 2030s or early 2040s. That's on budget and on time. That possesses the necessary architecture to achieve its observational goals without needing a starshade. That's fully refuelable and whose instruments are fully serviceable and replaceable. That could have a starshade added to it at any point in the future, and that quite possibly images enough Earth-like planets to discover at least one, and maybe even more than one, exoplanet that's actually inhabited. The big question that needs to go into the design of this telescope is the trade-off between how many Earth-like candidates it can directly image versus how large and costly the telescope is going to be. While the 6 to 7 meter range seems like the sweet spot, the nightmare scenario is that we build this observatory just a little too small and cost-conservatively to find what we're ultimately seeking, an inhabited alien planet. We must remember that in the search for life beyond Earth, we are playing a lottery with unknown odds. Each Earth-like planet that we image and characterize represents a ticket in a lottery where the odds of all of the prizes are unknown. Our chances of success depend entirely on which tickets are winners and whether we buy enough of them. The hard part is we won't know if we have meaningful constraints on what those odds actually are until after the findings from Habitable Worlds Observatory come in. And so it's up to us to build it in such a way that our odds of at least one success are as great as possible. If we do, we might finally have the answer to, are we alone in the universe? Just maybe, we'll know for certain that the answer is, no, there are others. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.